So today what I'm going to talk about is a 3D implementation. So far whatever we have talked about was 2D structures and how we can implement them in WebGL. And if you noticed, whatever we used the texture coordinate system that we were using so that we could implement everything in 2D. So basically, our data structures were 2D images that we were dealing with. And we want to know what we can do when we have a 3D structure, where instead of dealing with pixels, we actually have voxels that we need to be taken care of. So basically, as you can see here, you can have divisions in the X and Y coordinates, and you can actually have slices, certain slices in the Z coordinate system. But this requires usually a 3D array where people are usually familiar with and they are using. But what we use is actually we keep using our 2D data structure that we had because 3D textures are a little bit complicated to implement, but this one is relatively simple. That we start with the same 2D data structure that we had, but each of these Z slices that you can see over there, we assign it to a subsection of this matrix of the image. So the first Z slice would be in this corner, and then the next one would be in the following corner, and then next one, and so on and so forth. And then we follow in the direct next row of the Z slices. And in the end, we would end up with mx divisions in the x direction, m divisions in the x direction of the texture, and m divisions in the y direction of the texture. And basically this black structure that you see here is one giant image that we are going to deal with, where each of these subsections is representing one of those slices. So within each of these subsections, you can have an x and y coordinate that runs from 0 and 0 in that coordinate and 1 and 1 in that coordinate. So somehow we need to map whatever we had. So we had implemented a pixel coordinate or CC coordinate that we had 0 and 0 in this coordinate and 1 and 1 in that top coordinate. We need to be able to go, if you want to properly do these simulations in 3D, we need to be able to go back and forth between these two structures. If we had a pixel here, we need to be able to find out what is the representative voxel in 3D. And if we had a voxel coordinate, we need to know where in the 2D data structure we would end up. That is required because if you wanted to do finite differencing, you could imagine you would require to know the neighbors on the left, right, front, back, and up and down sides of this particular voxel that we have here. So whatever voxel we have, we need to know what is the voxel that is on these sides here and up and down, so that we could do at least some sort of finite differences on that. So we need to be able to jump between these two coordinate systems. So basically what I started with this code here is it's basically the same code that we had before, the same Pizza Nagumo code that we finished up in the last session. I have added some additional information into the environment. This mx variable is basically the number of z slices in horizontal direction. And this is the number of z slices in the vertical direction. And this nx and ny is the resolution in x direction, and this ny is our resolution in y direction.
So Abuzar,
Yes.
this number of z slices, I can't really visualize this. So I know a slice is for a given fixed z coordinate, right? But then what is the number of slices in a, let's say, a cube?
So in the cube, you can see in the cube that we have over here, we would divide it into a bunch of slices. So let's say this is the add some additional this. Maybe we had another slice over there, another slice over there, another slice over there. Each one of these is basically a division in the z direction. So totally we have one at the bottom, 2, 3, 4, 5, 6, 7, and 8 slices totally in the z direction. Total z slices that we are making. So each of these cubes then would become a voxel, right? So each of these cubes then would become a voxel of data. But instead of representing the data with the voxels, actually the voxels are defined a little bit differently from these ones to make it a little bit simpler. So let me just through. The voxels are actually from their boxes like this. This one is the center of that pixel on that z slice is the center of the voxel, and then the next one would go like that. And the center on that z slice, the center of the pixel on that z slice would represent the center of the voxel. So instead of imagining all of these 3D cubes, which becomes a little bit difficult, is easier to just represent the central slice of that voxel as one of these pixels that you can see on each of these slices. Okay, so each of the pixels is basically representing one voxel. Each pixel on the 2D image represents one voxel. And then we start stacking these slices that we have. Each of these slices is also is represented by a bunch of pixels, as you can see in this middle blue one that I hashed before. And then you put the first one, the first Z slice at the bottom in this corner. Then you stack the next one on the right hand side of it, and so on and so forth. You stack them together. You can technically put them all in a single line. So you're stacking them all in long data structure. But the reason that we don't do it and we just put some of them at the bottom of the other one is that the data structure doesn't become too narrow, because there are size limits on how big a texture can be in each of these directions, because this will eventually go up on the GPU hardware. If it's too long on one direction, it will not fit. It will not fit on the GPU. So what you need to do is to actually put this one in the two directions. So you break it a little bit so that you don't end up with a very slim data structure. And the parallelization would be a little bit more more efficient.
Okay.
Can I ask, that I guess makes sense if it's some like artificial constraint that the GPU is just expecting it 2D and is better optimized for that. But like in logical memory, even the 2D textures are contiguous blocks of memory, right? It's not like it's doing double dereferencing or anything.
It's actually a 2D data structure, because if you look at the data structure of the GPU, when you want to process it in the end, it will be mapped to the GPU. All the GPU have access to everything, but eventually you have arrays of subunits that are doing the calculations. And these arrays of subunits are actually put on a 2D matrix. So, and they have some sort of 3D structure to them as well, so that some of them can easily communicate with their neighbors, but they actually have a 2D structure.
Okay.
What the underlying hardware is exactly doing is very much dependent on that particular hardware that you have, but generally speaking, there is a size limit on the data structures that you have, at least in languages like WebGL and OpenGL. In CUDA, it allows you to just utilize the memory. It just creates a memory buffer that you can put it as like one-dimensional, and the entire thing can be put on a one-dimensional array. With what we are doing with the textures, I know that textures have size limits. So you can check out the size limit of the textures, I think, on each of these hardwares that you are using. Our limitation here is that we are using textures to represent our data. Does that answer your question?
More or less, I think so. Thank you.
Okay, you're welcome. Okay. So by resolution in X direction, what I mean is how many divisions you have in the X direction of your cube. By resolution in Y direction, what I mean is how many divisions you have in the Y direction of the cube. So the cube has the X direction, Y direction, and Z direction, and then you have this data structure that it has its own X and Y coordinate. So mathematically, they are two different coordinate systems. But I'm keeping these numbers small so that in the end, the simulations will not be too slow, and we can see some action on the screen. So then the width of this image that we are going to deal with is going to be the number of divisions that we have in the X direction of the cube times the M slices in the X direction that we are going to fit in the data structure. So how many pixels we have? For example, we have 5 pixels in each direction, and then we have 6 of those divisions. So the total data structure has a width of 30 units. In this particular scenario, 64 times 8. And then for the height, it's the same story. The the number of divisions that you have in the y direction of the cube times the my slices that you have in that direction. So in this picture, 4 wanted to multiply times 1, 2, 3, 4, 5 divisions in the y direction that we have. And then our data structures are just like before that we were dealing with, and our initialization sequence, I've set up the solution everywhere as 0, so we are not going to change much. The plotting algorithm has changed into this utility that we have, which is called the volume raycaster. The information that it requires is that which channel you want to plot. Change that one to the red channel of the texture. How many steps you want to do in the volume raycasting algorithm? So 100 steps. I can talk about this one in detail later on if you're interested. And then what is the minimum value of the data that you are going to represent, the maximum value? And I use some sort of thresholding so that the entire domain is not just colored. So certain part of the color domain that is just activated is going to be plotted. Original scaling is 0.7 so that the domain is just shrink down so that the entire thing fits into the screen, and the canvas that is going to be used is canvas 1. The render algorithm exists on that, so if you just change the plotting algorithm to this volume raycaster, it should be able to plot the solution of this simulation. So in the uniform sections, I've added these divisions in the x directions, or resolution in the x direction of the cube, resolution in the y direction of the cube, number of z slices in the x direction and y direction, and these are integer values that I'm sending as uniforms into the cube. So now let's see how our shader starts to change. Is this font big enough for everybody to see?
It looks fine to me.
Yeah, I think it's good.
We go to our shader that is here. I've already implemented some of the functions. Time consuming. We wouldn't be able to finish today's class. These are the uniform of integer type that we are bringing, mx and my, and x and y. You could also write all of them in a single line, like and doesn't matter. All of them will be imported. One utility that we would require is that we want to know what is the voxel coordinates if we pass in the pixel coordinates. So if we pass in the pixel coordinate here, for example, for this pixel, we want to be able to see what voxel is representing in the 3D cube. So for some reason, when I don't remember the exact reason that I chose this system, that I'm choosing stacking Z slices from the top and traversing them to the bottom. If you had actually put them from the bottom to the top, these functions would be a little bit simpler. I think the original volume raycaster that I copied from the internet, somebody had published a paper and they had an original volume raycaster that I modified significantly later on, was using this data structure from the beginning, that the Z slices were changing like so, as you can see here. And I never changed it, or I don't remember. I vaguely remember there was another reason, but I can't remember exactly what was that reason behind it. But what happens is that you have to figure out in which of these basically slices you end up. So these sections are for that part, and then you subtract basically what is being subtracted. Maybe I put this one side, but the coordinate, the pixel coordinate goes from 0 and 0 here and 1 and 1 in that corner. 1 and 1 in that corner, and we want to figure out the x and y coordinates. So the first thing that we do, we subtract the coordinate of this lower position from the x coordinates. So what remains is the remainder of that. And then what we need to do is, so this is this entire thing from this bottom left corner to that top corner is 0 to 1. We want to make sure that this corner is 0 and 0 in the voxel coordinates and is 1 and 1 in that coordinate. So that's why the multiplication by mx exists over there. So basically what was happening again, we had a coordinate in the pixel coordinate system. We subtracted the value of, we had a vector that was going from here to here, and a vector going from here to here. Find out what was that vector, we subtracted this part from this part. And then we scaled that part to, we scaled this one to change from 0 and 0 to 1 and 1. Part from 0 and 0 to 1 and 1. And then we figure out what is the slice number represent regarding that is corresponding to this part here. So the slice number is figured out here by doing a bunch of math, and then that slice number is also scaled, used to scale a float value between 0 and 1. The next value that we have is to get a pixel coordinate from a voxel coordinate. To basically, if we were given the voxel coordinate, what would be the corresponding pixel coordinate of that? So the x coordinate is pretty simple. Is we have to go the opposite route. First, we have to find out what is the z slice number. So the z slice number is first figured out, and then we figure out how many slices from the bottom here. How many slices in the positive vertical direction of the picture we have gone. This is how many slices in the horizontal direction. And then finally, the pixel coordinates are calculated here. The pixel coordinate x and so coordinate y. And then we implement a texture 3D function that if we pass a sampler and a voxel coordinate, So the sampler is a 2D structure, remember. We pass a voxel coordinate, it would return the pixel coordinates of, it would return the value of the voxel on that data structure. So this is the part that actually enables us to be able to see what's happening in each of the voxels. So the first thing that I want to do is I want to make sure that that everything is working correctly. So let me bring these functions here on the right hand side. We have the get voxel coordinate function there. What we first do, let me also comment out all of these parts that we were doing in 2D. First thing that I want to do is I want to figure out what is the current pixels coordinate in the voxel coordinate system. So I get the voxel coordinates of the current processed pixel. And I want to make sure that everything is going correctly. So I check out whether the length of this voxel coordinate is less than, if it's less than 0.1, I set the u variable to be 1. So let's have a look. This code, class code. So if I run this code and there are no compilation errors, which there are none, this corner of the domain should be activated. You see that that corner is activated. You can play with the size of that, maybe half of the domain. You can see that we have a quarter sphere of activation in that corner when we run it. So it's good, everything is working. What we need to do is we need to implement the Laplacian operator. So right now it's 0. Previously, if you remember, we had the texture function that was reading the sampler, with texture, I guess, and it was cc plus ii minus ii and so on and so forth. Here we want to work out our neighbors based on our 3D coordinate. So we replace this one with texture 3D and the center pixel with the center voxel coordinate. That would make our life a little bit easier. And the I and J vectors, you can see that I've changed them to 3D vectors now. This is the vector of moving you one voxel in the x direction, one voxel in the y direction, one voxel in the z direction. So the reason that I'm subtracting a 1 from that is that the voxels that we talked about, remember that the x divisions, if we had, let's say, 5 divisions here, 2, 4, 5, you had 1 pixel here, 1 pixel here, 1 pixel here, and 1 pixel there, so on and so forth. For the voxels, the number of slices that we're going from the bottom one, 1, 2, 3, 4. Maybe I shouldn't be subtracting a 1 here. I think that was a typo there. There shouldn't be a 1 there. But there must be a 1 here. Remember, if I remember correctly. Leave it as it is for the moment. I don't want to mess with it. Then we go back to it and see. Because I've tested the other version and it was working right now. So this is the voxel width in the k direction. So we would have that one. You have to go 1 pixel to the right, 1 pixel to the left, 1 voxel to the left, sorry. 1 to the back, all of these ones, and then replace them with the appropriate one. Plus JJ minus JJ plus KK and minus KK. And then I have to subtract this time 6 times the value of the center, which was just the color. We have already read it, so we don't do it again. And I've changed the pacing protocol to be pacing from the corner of the voxel. So let's see what happens. You see some activations traveling, but something is happening that you can see. Is not doing everything correctly. And the reason being is that previously we were just relying on the filtering in the textures to apply the boundary conditions for us. But here we have actually the ability to move out of the slice, to move out of the cube when we are shifting up and down in these ones. So what we need to do is actually apply the boundary conditions, and we can apply the boundary conditions here by making our life a little bit easier by checking whether the voxel is inside. If the voxel is outside, we apply the ghost rules that the filter was doing for us in the 3D space. So CX needs to be a positive number. The x coordinate of our voxel needs to be a positive number. If it was positive, we can return whatever it was. Otherwise, we have to mirror it. It means that we went outside the domain, so we have to apply the boundary conditions there in the x direction. We have to mirror it. We can do the same thing for y and z directions. All of them need to be positive. Copy it like this. So this is doing the mirroring with the bottom left and front boundary. We want to do it for the back boundaries as well. So CX needs to be less than 1. Maybe I should show a little bit of why I'm doing this. Background. So if you're on the x coordinate, let's just look at the x coordinate. This is the end. This is the node that we are considering. This is the last pixel, basically. The center of the pixel is here. And if we want to read the center of the pixel outside, there won't be anything. So clamp to the edge, which was applying, I think, first order approximation for us, was copying, was considering that this must be, the same value must be used here. So whatever value that we had here, if we wanted to find this one as a ghost node, we would use and copy that one to there. And the reason being was that if we had ui plus 1 minus ui divided by delta x equal to 0, then ui plus 1 must be equal to ui if we want to set that boundary condition to 0. Now, if that coordinate is 1, what we need to do, we want to know how much we went further, that delta x, which is coordinate of that point, d dot x minus 1, and we want to subtract 1 from that because we want to move delta x exactly back so that we end up reading the value over there. So it would become 2 minus dx in the end. So what we return here is that if we were less than 1, we just return cx. If we were more than 1, we return 2 minus. We do the same thing for y and z directions. Copy that, paste it here, it here. Let's have a look and see if this one was fixed. Last part that you see on the top is an artifact of visualization. It's not actually an activation on the top. Pause that, and then we can check out if this one was necessary. I think it's not necessary. I think it's not necessary. It doesn't make that much difference. So that shows how we can do 3D simulations. So with the interactions, basically what we need to add was, I will show in the next session how we can add more interactions to the 3D code. Maybe we can do, we can start playing with the visualization. We can bring these structures in. I still don't know what are these artifacts. You see that sometimes they show up. But he is willing to fix these artifacts. Would be very happy. They come from the volume raycaster. So that's how we do the 3D simulations in using a 2D data structure that we still can utilize. It would be nice if we had a proper 3D structure, data structure, but I think this provides an easy method of access for simulations. Now, do you have any questions or concerns, doubts?
Do 3D data structures just not exist in WebGL, or are they not convenient for us to use for some other reason?
There is a texture 3D. There wasn't at the time that I was implementing, there wasn't a proper documentation on it that how exactly is the texture 3D working. I'm also not sure if the 3D textures are renderable. You need to be able to render to that data structure, not only be able to read from the data structure, but you should be able to read to the same, to write to the same data structure. And I think that 3D 3D textures are not renderable. You can just do filtering on them. If you have a 3D data structure, uh, you can read from it, and you can do interpolations between the values and things like that. But you're not able to render to that 3D structure. There is a concept of texture arrays. Also, again, the problem of writing to the texture array. I haven't figured out a way of doing that. Simplest thing to do was this method, and it was good enough, and it was fast enough to do the work that I wanted to do. But if you're interested, you can look into those problems and see how they are implemented. And if there is a way to work with 3D textures or to write to 3D textures, I'm not sure if the support is there to write to 3D textures. There is also texture arrays that you could have an array of textures, and then it would remedy some of the problems that arise due to using 2D textures. But I'm again not sure how you can render to a texture array. You can look through it and see if you can find anything about it.
Okay, thank you.
You're welcome. This visualization algorithm can be improved a little bit. Let me see if I have. I think there were some stuff that I've turned off here. There are some options. They're doing things like I think can add some lights. I think you need to have some light, some lighting. But it has a bunch of features. This raycaster, there's a possibility of showing these slices, excess slices, and move them around. It is possible to show filaments, see what's going on. We can modify the click algorithm so that you can actually click on this cube and send out activations in there, so that you can initiate a scroll waves. We don't know what that artifact is at the top corner that is showing on. It's the raycaster that is used for the visualization can benefit from a lot of improvements. The algorithms that are calculating shadows. One thing is that you're casting a shadow on the previous one. The direction of the light is somewhere from there, or from behind. Right now, there are few light points, 4 sources of light. One from the Y direction, one from the negative X direction, one from the Z direction. From all directions, it is being lighted up. you can improve the visualization. I think those are the parts that can benefit from improvements significantly. Be the solution. The other part, as I said, is the data structures. If you can find out the replacement data structure and try it and see how the performance changes, it would be nice. Okay. Any questions?
So to summarize how the 3D or the 2D data structure works for displaying 3D, it's one big 2D data structure that holds multiple slices in a row, and then that you map it onto the canvas to display in 3D.
Mm-hmm.
Okay. Gotcha. Thank you.
You're welcome. Any other question?
I know you said this, but my brain, for some reason, elided it. So the NX and NY were 64 and 64, and then the MX and MY were 8 and 8. So that's saying that each Z slice is 64 by 64, and then you have
Correct.
8 slices in each horizontal. Okay.
Yeah, and
All right.
totally you would have a cube that is 64 divisions in the X direction, 64 division in the Y direction, and 64 divisions in the Z direction, because there were totally 64 slices.
Right. Thank you.
You're welcome. Any other question? Oh. Stop the recording.